Hey guys, welcome. This is 8.2 inverse trig functions. Okay, so 8.1, well 6.2 and 8.1, we refreshed on one-to-one functions and inverses. And in 8.1, we learned the inverse trig properties for sine, cosine, and tangent. Now we learned the properties for the remaining three, cotangent, secant, cosecant. Okay, before we start, let's just get a little warm up here. Okay, these are some fun ones. We want to solve exact value expressions involving inverse trig functions. So here says, find the exact value of the sine of inverse tangent of 1/2. So the way we handle this is we make a small substitution. We let theta equal the inside trig function, the inside trig expression. So we let theta equal the inverse tangent of 1/2. And you probably know where we're going with this now. Then compose both sides with tangent. Then tangent theta equals 1/2. But this can only happen on the inverse tangent restrictions. On parentheses negative pi over 2 to pi over 2. So what we do that information is now we plot it on the unit circle, but we only plot it on the restrictions for the inverse tangent on the unit circle. The inverse tangent restriction unit circle, however you want to word it. Okay, so here we go. We plot that, and here are the restrictions, negative pi over 2 to pi over 2. And now 1/2 happens to be positive. So this 1/2 is positive, which means we have to be in quadrant 1. Because remember, the inverse tangent lives in quadrants 1 and quadrants 4. So if this value of 1/2 is positive, this means we must be in quadrant 1. Okay, so we draw a right triangle. There's that. Here's my theta. And if tangent is 1/2, remember tangent puts opposite over adjacent. So the height will be 1, the base will be 2, and by Pythagorean theorem, the hypotenuse should be the square root of 5. Okay. So now we have our right triangle within the restrictions of the inverse tangent function. And we did make a small substitution in the beginning. So that's what we're going to go back to. We're going to go back to that substitution. So this is what we're going to look at again. Okay. So actually, let me move myself up here. There we go. Okay. Okay. So that's what we're going to look at, which means that this, put a lovely little green arrow, right? Let me do this. I have room. So this comes back, and we get sine of theta, because theta now contains all that information. Theta contains all of this information that we created based on the right triangle and the restrictions. So that's what theta now contains. So now all we have to answer is, what is the sine of theta? What is the sine of this theta value in this triangle in these restrictions on the unit circle. Okay, so we look at it and we know sine puts opposite over the hypotenuse. So sine of that theta puts 1 over the square root of 5, and we know rationalize b proper. We get the answer is the square root of 5 over 5. That's it. That's how you handle this. We make a small substitution. Okay. Let's try it again. So find cosine of the inverse sine of -1/3. Once again, let all of this inside equal theta. Theta is going to contain all that information. Okay. All right. So let theta equal, not that. Behave today, please. Let theta equal the inverse sine of -1/3. Then compose both sides with the sine function. Then sine theta is equal to -1/3, but this can only happen on the inverse sine's restrictions. -pi/2 to pi/2. And again, what do we do with this information? We put it on the unit circle. And the unit circle only involving the inverse Trig's restrictions. So here's my unit circle. Here is -pi/2, pi/2. Now remember, the inverse sine function lives in quadrants 1 and quadrants 4, just like the inverse tangent above it. The only difference between the two is that pi/2 and -pi/2 are included. Okay, so now come back and look at this value for sine. That is -1/3. So does that mean we are in the first quadrant or the fourth quadrant? Where can sine be negative at? And if you picked the fourth quadrant, you are correct. Okay. So this means our triangle goes in the fourth quadrant. Here's my theta. And since this is the sine function, sine puts opposite over hypotenuse. And since we are in the fourth quadrant, the height's going to be -1. And the hypotenuse is going to be +3. And then by Pythagorean theorem, we should get that the base is 2 square root 2. That's 9 minus 1, so 8, yes. Okay, so now remember, theta contains all this information in the triangle. All of this belongs to theta now, which means we come back to our substitution. This becomes cosine of theta. Cosine of theta. Now, all we want to know, what is the cosine of this little theta right here? What is the cosine of that theta? Well, remember, cosine puts adjacent over hypotenuse, so our answer is 2 square root 2 over 3. That's it. Nothing to it. Okay. Hooray, fun, right? Okay, let's do it again. let all of this equal theta. Let all of that equal theta. Whoops. One moment. Ooh. Okay. So again, handle this the same way. Let theta equal the inverse cosine of -1/3. Okay. Then, of course, compose both sides with cosine. Cosine theta equals -1/3. But this can only happen on the inverse cosine restrictions. So this can only happen on 0 to pi. Now again, what do we do with that information? We put it on the unit circle dealing with the inverse cosine's restrictions. Here's my unit circle. Here's 0. Here's pi. I could even put pi over 2 in there because it's included. And now remember, the inverse cosine lives in quadrant 1 and in quadrants 2. Okay, now look back at our value here. Cosine theta is a -1/3. So what quadrant are we in? Are we in the first or are we in the second quadrant? Where is cosine negative? And if you picked the second quadrant, you are correct. Okay? So that's where we're going to put a right triangle. Here's my theta. And cosine puts adjacent over hypotenuse. So this means if it's -1/3, the base is -1. The hypotenuse is 3. And by Pythagorean theorem, again, the height over here should be 2 square root 2. Square root 2. Okay, now come back to our substitution. This now just becomes the tangent of theta. And remember, theta contains all this information in that right triangle, right? Theta contains all that information. So we want to know what is the tangent of this little theta right here. And the tangent of that, oops, there we go. And the tangent of that theta is going to put opposite over adjacent. So 2 square root of 2 over -1. Or it's just going to give me -2 square root 2. There it is. Okay, these aren't bad. You just have to know the restrictions that you're dealing with on the unit circle for the specific trig function. Okay, specific inverse trig function. Okay, last one on this page. This one's handled a little different. This is the inverse sine of the cosine of 5 pi over 6. Everything else has been tangent of an inverse function. This one is the inverse of cosine. Okay, well, this is not too bad. I mean, sure, we could still make this a substitution. We let theta equal the cosine of 5 pi over 6, right? We let theta equal the cosine of 5 pi over 6. Theta equals the cosine of 5 pi over 6. Okay, and hopefully no need for an inverse trick, because all you have to do now is look at your unit circle and what is the cosine of 5 pi over 6. The cosine of 5 pi over 6 should be negative square root 3 over 2. Okay. So now we come to our substitution. This becomes sine inverse of theta. Oops, just keep it green, right? Sine inverse of theta. Well, theta happens to be negative square root 3 over 2, right? That's what theta happens to be. Move up a bit. So that's all you have to do is plug in. You say the inverse sine of negative square root 3 over 2, which means we look at the inverse sine's restrictions on the unit circle. I'll draw those really fast. So here's where the inverse sine lives again, negative pi over 2 to pi over 2. Over there, 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 and there. There's 0. There's pi over 6, negative pi over 6, negative pi over 4, negative pi over 3, pi over 4, pi over 3. Okay. And all we have to ask ourselves is, well, what radian value gives me negative square root of 3 over 2 on these restrictions? Well, first off, if we are negative, this means that we must be down here in the 4th quadrant. So what is the inverse sine of negative square root of 3 over 2? Remember, this is calling on the unit circle backwards. We put in a numerical value. The output should be a radian value. And which radian value gives me negative square root of 3 over 2? That is going to be negative pi over 3. So sine inverse of negative square root of 3 over 2 is negative pi over 3. That's it. That's how we handle that one differently. All right. Moving on. Feel good? I feel good. It's Monday. By Thursday, I'm like, but it's Monday. Okay. So let's get into the properties of the inverse secant function. Here is the secant function, and of course, if you drew a line through it, it is not one-to-one because we intersect an infinite amount of times, right? Infinitely many times. So again, we know it's possible to restrict a function to become one-to-one, and the popular restrictions for secant is going to be from 0 to pi over 2. From 0 to pi over 2. Those are the most common restrictions, and those are what's listed below. All right. So the restricted secant function on the left side, this is what we restricted to. The domain is from 0 to pi, where x cannot equal pi over 2. That is because pi over 2 happens to be a vertical asymptote, right? So, oh, did I say pi? Whoops, I cut that off early. Okay, my bad. I know what I did. I said 0 to pi over 2. Your restriction should have been 0 to pi. There you go. I mean, 0 over pi over 2 would have worked, but the most common restrictions are 0 to pi. Those are what's written below. So that's my bad. Okay, so back to it. So on the left side, the domain for secant 0 to pi, where x cannot equal pi over 2 because that is a vertical asymptote, and the range is from -infinity to -1 and 1 to infinity. Now, for the inverse secant function, you see there on the right side, y equals the inverse secant of x, and remember when you find an inverse, your domain and range switch places. So this domain goes to your range, this range goes to your domain. So they just flip. So now the inverse secant function, his domain is -infinity, -1, then 1 to infinity, and its range is now 0 to pi, where y cannot equal pi over 2, because once you have an inverse and you flip everything, a vertical asymptote now becomes a horizontal asymptote. So that's why it's y equals pi over 2. Okay, perfect. Okay. Now, down here, this is the most important part, because this is what we want to reference when dealing with our inverse trig functions. So we are going to show where the inverse secant lives on the unit circle. And our restrictions, we said, were from 0 to pi, where pi over 2 is not included. Okay. So here's 0. Here's pi over 2. And I'm going to put a little dashed line here indicating we cannot use pi over 2. And the inverse secant is just like cosine. It lives in quadrants 1 and 2. And here are the trig values, or not the trig values, but the radian values. Pi over 6, pi over 4, pi over 3. Two pi over 3, 3 pi over 4, 5 pi over 6, including 0, including pi. So once again, this is where the inverse secant function lives, right? This is where the inverse secant function lives. So this is the unit circle for secant inverse of x, right? All of these values is where the inverse secant lives. So this is what you want to reference. Okay, so that's the inverse secant function. Okay. Look, we're moving on. Yeah, this one's fast, right? No messing around. Now we're into the inverse cosecant function. All right. Inverse cosecant is just like secant. If you draw a horizontal line through it, you intersect it infinitely many times, which means it is not 1-to-1. But we can restrict the cosecant function to become 1-to-1. And the most popular restrictions are negative pi over 2 to pi over 2. If we restrict it to this domain, then it becomes 1-to-1. And did I get that right? Yes, they're right there. And of course, x can't equal 0 because x equals 0 is a vertical asymptote. Okay, perfect. So we restrict that domain. The cosecant function becomes 1-to-1, which means it has an inverse. We find the inverse, which is over here. Y equals the inverse cosecant of x. And remember, your domain and range will switch, will flip, will swap, whatever you want to use. So this range becomes the domain, that domain becomes the range. Okay. All right, and down below, again, this is the range we want to follow. These are the unit circle restrictions we want to follow for the inverse cosecant function. And remember, if it went from x equals 0, not equal to 0, to y not equal to 0, this means when you found the inverse, it went from being a vertical asymptote to a horizontal asymptote, which is right there. Okay, cool. We're moving. Again, to the most important part, this lovely unit circle for the inverse cosecant function. So we live from negative pi over 2 to pi over 2, where y can't equal 0. Okay, so that means we are down here, negative pi over 2 to pi over 2. There's 0. I'm gonna put a dashed line saying we can't use 0. And since it's the inverse cosecant, since it goes from negative pi over 2 to pi over 2, we live in quadrants 1 and 2. 1 and 4. All right, 1 and 4. Okay, so here are the radian values we can use. Pi over 6, pi over 4, pi over 3, even including pi over 2. Now just reflect these values and we have the rest of them. Negative pi over 6, negative pi over 4, negative pi over 3, including negative pi over 2. So once again, this is the unit circle for cosecant inverse. Okay, the unit circle for cosecant inverse. This is where the inverse cosecant function lives. Okay, so this is where it lives. And it shares very similar restrictions to the inverse sine function. Wink, wink, hint, hint. Building up to something bigger, okay? Not too much bigger. It involves a calculator. Boring, right? I know. Okay, so that's everything you need for inverse secant. Oh boy. Inverse secant, inverse cosecant, and last is the inverse cotangent. Okay. Well, just like all the other functions, if you draw a horizontal line through it, you intersect it infinitely many times, which means it is not one-to-one. Is it possible to make it one-to-one? Yes, we have the power. This is the only time we get to manipulate math and say, hey, I'm going to do what I want, math. I'm going to make this function one-to-one, whether you like it or not. See, that's the beauty about it. We get to do it as long as it makes sense. Okay, so the most common restrictions for the cotangent function are going to be from 0 to pi, right there, 0 to pi. And it just so happens that 0 and pi are both vertical asymptotes. That's where our domain comes in down there. 0 to pi, parentheses, not included. Okay, so there's that. And if we find the inverse, there's the inverse cotangent function. The domain and range, again, flip, switch, and switch, right? And the only things we're really worried about is just the restrictions for the unit circle. So the inverse cotangent function lives from 0 to pi, where 0 and pi are not included. Okay, and you see that, let me erase some stuff. There you go, there you go, there you go. And you see that these vertical asymptotes now become horizontal asymptotes on the inverse. Okay. You're so lucky we don't have to graph these. If we did, this lesson would probably be a lot longer. So just be glad. Okay, so the most important part of all of this, remember, okay, finding out where the inverse cotangent lives. And we said that we live from 0 to pi. So here's 0, here's pi over 2. And the inverse cotangent lives in quadrant 1 and 2. But we cannot include 0, and we cannot include pi. All right. Pi over 2 is definitely included. Okay. And just like the other ones, list the radian values we can use. Pi over 6, pi over 4, pi over 3, 2 pi over 3, 3 pi over 4, 5 pi over 6. And remember, for all of these unit circle restrictions, you can use any radian values between these angles as well, as long as it fits in the quadrants. Okay, this is the unit circle for the inverse cotangent. This is where it lives, and it shares very similar restrictions to cosine, right? It shares very similar restrictions to the inverse cosine, and it also shares similar restrictions to the inverse secant function. So those are some things to think about. Okay. So there's that. It's lovely. And now we get into some calculator work. Okay. So use a calculator to evaluate inverse secant, inverse cosecant, and inverse cotangent. Well, if you don't have a super calculator, this means you don't have a secant inverse button. And most calculators don't even have a secant button. If you're using this lovely guy here, you don't have any of those buttons. If you're using a graphing calculator like a TI-84, you still don't have a secant button. So we have to figure a way how to compute this in our calculator by creating some type of similar application. So that's what we're going to do now. So the inverse secant of 3. How do we type this in a calculator? There's no secant button. Yes, 1 over cosine is secant, but that's not the same as the inverse. So with that being said, we are going to handle this like we handled the problems on the first page. We are going to create a substitution, okay? We're going to create a substitution. So let's go ahead and say let theta equal the inverse secant of 3. Then compose both sides with secant, right? Compose both sides with secant. Secant theta equals 3. But secant theta can only be equal to 3 on secant's restrictions. And secant's restrictions are from 0 to pi. That's what we just learned today. So if we go back up to the inverse secant function, right there, it lives from 0 to pi, where we can't include pi over 2. I don't think we necessarily need that part, though. We just need to know 0 to pi, okay? All right. So with that being said, we want to type this in the calculator. So we need to find a function in our calculator, a trig function in our calculator that could share similar restrictions and a similar quadrant, right? A similar quadrant. Okay, well, it just so happens that another function who shares these restrictions, right? Another function who shares these restrictions happens to be the inverse cosine. The inverse cosine lives on these same restrictions. So now we have to figure out, how can we rewrite secant theta equals 3 into an equation for cosine? Well, the answer to that is by identities. I hope you remember your identities, because when we get to 8.4, it's gonna get ugly. Okay, so remember that secant is the same as 1 over cosine theta, and we still set that equal to 3. Okay, well, this means that if I want to solve this equation for cosine, so now we think algebraically. We just use a trig identity, and now we have to think algebraically to rearrange this equation in terms of cosine. Well, it's quite simple. I can put that 3 over 1, and we can go back to elementary school and cross multiply, right? We cross multiply evil, evil butterfly with the claw of cross multiplication. Okay, all right, so we can cross multiply. Let me get rid of all that by butterfly. And this becomes 3 cosine theta equal to 1. Then divide by 3. Cosine theta equals 1/3. We're almost there. We need to put it as the inverse. So we need to write this as the inverse. So what we do with cosine theta equal to 1/3 is we compose both sides with the inverse cosine function. That's it. We compose both sides. So we'll start again. This becomes theta equal to the inverse cosine of 1/3. And voila, we're there. If you look at your calculator, is there an inverse cosine button? There is. All you have to do is hit secant and cosine, right? Shift and cosine, and it should give you the inverse cosine of 1/3. We have that button now. But before you start calculating stuff, make sure that your calculator is in radians. Put it in radians. And with that being said, theta is equal to, I'm going to go there, mode, I'm in radians, secant inverse cosine of 1/3, hit enter, and I'm going to do this in 2 decimal places. We get 1.23. Yay. Okay, perfect. So before moving on to the next one, what you should notice now is that we've actually created a formula to take any secant values and change them into cosine values. And what would that formula look like? We would look something like this. We would say inverse secant of any value of x is going to be equivalent to the inverse cosine of 1 over x. And this is a formula you can use anytime to convert a numerical inverse secant value into a numerical inverse cosine value. So that means that we did all of this for the formula. You don't have to repeat any of this. You just come to this formula and you type it in. So we had the inverse secant of 3. The inverse secant of 3 became the inverse cosine of 1/3. That's it. That's a lovely little formula we just created. It's awesome. Okay. Perfect. All right. Cool. There are a lot of other ways to handle this as well. I can get into later. It involves the unit circle, and it involves matching restrictions with the inverse trig functions. It gets really cool if you want to play around with it, but this formula keeps it really simple. Okay. All right. Cosine, cosine, cosine. Yeah, there you go. That looks like an S. Okay. Let's do it again. Which means we can guess on this one, but let's figure this one out step by step, because if it's cosecant, then, well, you know that its inverse or its reciprocal function is sine, right? But we'll get there in a second, because again, the lesson is, do you have an inverse cosecant button on your calculator? That answer is no, right? That answer is no. Unless you have the TI 5000, then yes, you do. But since you don't, this is how we handle it. We do the same steps as above. We say, let theta equal the inverse cosecant of -4. Then, you know what's next. Compose both sides with cosecant. Cosecant theta equals -4. But this can only happen on our new restrictions of cosecant. So we found those already. What are the inverse restrictions for cosecant? And cosecant, get out of here. Cosecant lives from -π/2 to π/2, where we can't equal 0. All right, so again, don't need to include that part unless you really want to. So we're back here. So this can only happen on -π/2 to π/2. Now we ask ourselves, what trig function shares these similar restrictions? What trig function, actually there's two, right? What trig function shares these similar restrictions? Well, the inverse sine does, and also the inverse tangent. I'm going to say let's go with the easy route and choose the inverse sine of x. Even though we can get the same answer using the inverse tangent. That's why I said earlier there's a couple more ways to do this, but I'll get into that when we get to the next two problems. Okay, so we're going to choose the inverse sine of x. So what we do with that is what we did above. We use identities. So cosecant becomes 1 over the sine of theta equal to -4. I put -4 over 1. I cross multiply, right? And we get -4 sine theta equal to 1. Divide by -4, we get sine theta equal to -1/4. And now we need to get to the inverse sine function. So you compose both sides with the inverse, right? Which means theta is going to equal the inverse sine of -1/4. And now, do you have an inverse sine button on your calculator? Yes, you do. Hit secant, hit sine, and type in -1/4. And to 2 decimal places, I get -0.25. There it is. Okay. There you go. Okay. Before moving on, realize that we created another formula to quickly calculate any inverse cosecant value, right? Any inverse cosecant value. So this means that you have cosecant inverse of x is equivalent to the inverse sine of 1/x. There you go. So since we created this formula, you don't have to worry about doing anything you see on the left. Just use the formula, convert it, calculate. You're welcome. Okay. All right. Now here comes the tricky stuff. Tricky business here. Okay. All right. So I'm going to show you 2 ways to do this. So this is the many ways, right? So we're still going to handle this that we did everything above, right? Okay. So the inverse cotangent of 1/2. The inverse cotangent of 1/2. So again, there is no inverse cotangent button on your calculator unless you have a fancy one. So we go through the same steps. Let theta equal the inverse cotangent of 1/2. Then cotangent theta equals 1/2. But this can only happen on our new restrictions for cotangent, which is from 0 to pi, not included. 0 to pi, not included. Zero to pi, not included. Now, we ask ourselves, who shares similar restrictions to this 0 to pi? 1 is going to be the inverse cosine function. 2 is going to be the inverse secant function. Gross, right? Okay. So I bet you're guessing which one's the easiest function to go with, and that is correct. That is the inverse cosine of x. Now the real question is, how do we turn cotangent, how do we turn this cotangent into a cosine? Oh, and the answer here is definitely not identities. The answer here is by right triangles and unit circle restrictions. This one's going to be a lot different, so I'm going to take you the hard way first, and then we'll come back to the easy route, okay? All right. So this means that let's go ahead and create our unit circle for cotangent on these restrictions. So that's what we'll do down below. So we know we exist from 0 to pi. And if cotangent is positive, this means we must be in quadrant 1. So that's where this is going to go. Here's my theta. And cotangent puts adjacent over opposite. So this is going to be 1, that's going to be 2, and by Pythagorean theorem, square root 5. And now the answer on how you convert cotangent inverse of 1/2 into cosine. The way to do that is, well, find the cosine of our given theta. Remember, theta contains all the information in the triangle. So if I say cosine of that theta is equal to 1 over the square root of 5, well, all I have to do for theta now is apply the inverse of cosine and calculate. Believe it or not, that's it. So this becomes theta equal to the inverse cosine of 1 over the square root of 5. Why didn't I rationalize it? Because your calculator doesn't care. You can type it in your calculator just like this. And I'll put the squigglies there, and I get the inverse cosine of 1 over the square root of 5 is 1.11. Okay, well, with that being said, how do you make a formula for that? You really can't, right? You really can't do that, because we can't say, oh, the inverse cotangent of x is equal to the inverse cosine of x. Not even 1 over x, because the reason we can't make a formula for that is because this is 1 over the square root of 5, and that's 1/2. There's no reciprocal, there's nothing that makes those equal. So there's no formula for that at all. So the only process, the only formula you have is create the unit circle, draw the restrictions, and match the proper trig function that shares those restrictions. So here, if cotangent was 0 to pi, cosine is also 0 to pi. We don't want to use secant. We could use secant, but secant would be more difficult, because again, we don't have a secant button in our calculator. Okay, so there's one way to do this, right? And yes, we could have used this approach on the ones above it, but we didn't have to, because we used it by identities. We didn't need a unit circle. Okay, so here is option 2. Okay, here's method 2. I'll separate all this. Let's see. Method 2. Method 2. Okay, so here we're starting out again at cotangent theta equals 1/2 on 0 to pi. Okay, well, why not follow everything we've done above? Cosecant, sine, secant, cosine. This means that we should have a cotangent and tangent. Why not? They both work. So we want to try and force these restrictions on the inverse tangent function, right? The only thing about the inverse tangent is that it doesn't live on 0 to pi. The inverse tangent lives on negative pi over 2 to pi over 2. Well, there's an easy fix for this, okay? So I'm going to go back and draw our unit circle. All right. So remember, cotangent lives from 0 to pi. Cotangent lives from 0 to pi. So cotangent lives in quadrants 1 and 2. Well, our 1/2 here happens to be positive. So again, this means we have to be in quadrant 1. So we have to be in quadrant 1. Okay. So I'm just going to put my value of theta here in quadrant 1. I'm not going to fill up the triangle though, because I'm going to show you what I'm getting at. Okay. And here's pi over 2. Okay. So if we want to make the relationship from inverse cotangent to inverse tangent, we'll realize that the inverse tangent lives in quadrants 1 and 4, right? Down here is negative pi over 2. Well, if cotangent of 1/2 is positive, this means that it's in quadrant 1. And if we want it to share the same restrictions as the inverse tangent, well, this means if it's positive, this means that for tangent, it also has to be in quadrant 1. So basically what I'm saying is that the value of our theta is in quadrant 1. So cotangent and tangent are sharing a quadrant. So with that being said, we can do this by identities. Since they share a quadrant, I now get, where am I going? Let's see. I'll just come down here. So this means that, I'll rewrite this again. Cotangent theta equals 1/2. Now by identities, this becomes 1 over tangent theta equal to 1/2 cross multiply, and I'll just move it up here, cross multiply, and you get 2 tangent theta equals 1, where tangent theta equals, not 2 tangent theta. Oops, other way. Bad cross multiplying on my part. Racy. All right, proper cross multiplying, you get tangent theta equals 2. Apply the inverse, and theta equals the inverse tangent of 2. We have it. Do you have an inverse tangent button on your calculator? Yes, that is correct. So if I say secant inverse tangent of 2, well, guess what theta equals? 1.11. What do you notice about this value? It's the same as that value, just less work. Okay, so with that being said, we have created a formula to go from inverse cotangent to inverse tangent. But the only way this formula can work is if the numerical value of our trig functions shares the same quadrant, okay? They have to share the same quadrant, and that's how it's gonna work. So with that being said, we now have a new formula. It is inverse cotangent of x is equal to the inverse tangent of 1 over x. But this can only happen if x is positive. If x is positive. So that's our only restriction on this. And the reason I say it's if x is positive, because in quadrant 1, cotangent's positive and tangent's positive. In quadrant 1, inverse cotangent positive, inverse tangent's positive. So this formula can only work if x is greater than 0, meaning x is positive. So that's the only way we can use this. If you get a negative value, well, that's going to change the stuff. But now, again, here's your formula to go from inverse cotangent to inverse tangent. but it only works if the number inside is positive, okay? It only works if the number inside is positive. So once again, you can forget everything above it. Just use that formula. Use that formula I box. That's it. X has to be positive for you, in order for you to use that. Life is easy, right? Okay. All right. Last one. Let's see. The inverse cotangent of -2. Okay, so this property is not going to work. That's not going to work because the inside number is negative. So I have to show you a way around it, okay? I have to show you a way around it. Okay, so like all the other ones, we handle this the same way. The let part, the then part, you know how it goes. So let theta equal the inverse cotangent of -2. Then cotangent theta equals -2. Of course, on the restrictions, 0 to pi. On the restriction, 0 to pi. So down below, because we want to make this easy, we want to use the new formula from cotangent inverse to tangent inverse. So I'm going to show you the unit circle of what we have here. So here's 0, here's pi. If we're -2, what quadrant are we in? Are we in quadrant 1 or are we in quadrant 2? Quadrant 2 is the correct answer. You're right. Okay, so this means that my theta is going over here. Okay, well, here is the problem. If we want to use the inverse tangent lives in quadrants 1 and quadrants 2. I keep saying 2. I mean quadrant 4. So the inverse tangent lives in quadrants 1 and in quadrants 4. So we need to figure out, how do we get this theta back into quadrant 4? And the only reason I say it needs to go in quadrant 4 is because in quadrant 4, cotangent's negative and tangent is negative. Well, here's what we have to think about: periodic properties of our trig functions. Tangent repeats itself every pi, right? Tangent repeats itself every pi. So if I took this theta and add pi to it, guess what? It puts me in quadrant 4. This means my new triangle is in quadrant 4. And all I had to do was say theta plus pi. Theta plus pi. Which means that we have our new formula. We're going to use everything that you see up here. But now for the inverse tangent part, for the inverse tangent of 1/x, guess what you're going to add to it? You're just going to add pi. That's it. You're just going to add a pi. So our new formula here is going to be, let me write this down. Where are we? So this becomes, I need to get rid of that little thing. There you go. Okay. So all of this becomes, I get cotangent inverse of -2 is going to equal the inverse tangent of 1/2 plus pi. The inverse tangent of 1/2 plus pi. That's all we have to do. So now, plug this in your calculator, and we get cotangent inverse of -2 is equal to, and let me do secant inverse tangent. Oh, that should be negative in there. Inverse tangent of -1/2 plus pi. I get 2.68. There it is. So now we have one new formula, and that formula is the inverse cotangent of x is equal to tangent inverse of 1/x plus pi. But now, this can only happen if x is negative. So, x is less than 0. And there you go. Okay, there it is. Those are the 4 formulas you can use when calculating inverse trig values. There it is. There's only some restrictions on these 2. You can only use the first one if the value is positive, and you use the second one if the value is negative. Okay, cool. Let me see something. Secant inverse cosine of -2 over, let's see, cosine, but let's see, that'd be -2. That'd be 1, so it'd be square root of 5. Just double checking my work. 2.68. Okay, cool. I get 2.68 if I was going to do the first route of the whole make a right triangle, find a trig function that matches the restrictions. So if I did cosine of whatever I get in the unit circle on the last one, I would still get 2.68. But using these formulas is a lot faster. Okay. Keep going. Last one for all the marbles. Write sine of inverse tangent of u as an algebraic expression containing u. All right, so the way we handle this one is how we handled everything on the very first page, right? Or maybe just handle everything today by making that small substitution. But now there's no numbers, there's only letters. So, inverse tangent of u becomes theta. So, let theta let theta equal the inverse tangent of u. Then tangent theta equals u on the inverse tangent restrictions. -pi/2 to pi/2. Okay, and like I said, we're handling this like we did everything on the first page. Then I will draw my unit circle. I got room, right? I'll draw my unit circle for the inverse tangent. -pi/2 to pi/2. And the value for tangent is a positive u, which means we must be in quadrant 1 on the inverse tangent restrictions. okay? So this means that my theta will go into quadrant 1, and tangent is u. So what I'm going to do is I need to label the triangle, so I'm going to make u into a fraction. I'm going to put u over 1. And remember, tangent puts opposite over adjacent. So now we know how to label my triangle. The height will be u, the base will be 1, and by Pythagorean theorem, we should get the square root of u squared plus 1. The square root of u squared plus 1, right? This would be u squared plus 1 squared equals c squared, and you still get u squared plus 1 equals c squared, which would give you the square root of u squared plus 1 equal to c. So that's where that comes from. Okay, now we're almost there. Oh, I'm not even writing that big. All right. So this means that, bring this in. So take this whole substitution and we're coming over here, which means I now have the sine of theta. And remember, theta contains all of this information. So all we want to know is what is the sine of that actual theta? And that sine value is u, opposite over hypotenuse, square root u squared plus 1. That's it. Nothing more. It's all in terms of u. That's everything we did on the first page today. I guess I could have wrote bigger. Oh well. Okay. There it is. Know your inverse trig functions restrictions. That helps you find out where they actually exist.